Okay, another short chapter that we'll learn in a week and then we'll test next week. Yeah, but 3 of the concepts we're covering today, all in a day, and they're not that bad. What? Yep. All right. I'm teaching them all right now. So we're doing derivatives in context of, we're doing derivatives where it relates to position, velocity, acceleration, rate of change. Okay. So if you have a position function, okay, if you have a position function, so that might be like the height of an object, that might be h of t and equals some function, okay? If we take the first derivative of the height, first derivative of the position, that's how fast it's going. So that would be the velocity of the function. So if you throw a ball up in the air, the height of it would be the original equation. How fast it's going would be the first derivative. So the height would be the velocity function. Okay. And then if you take the second derivative of the height, that would be the first derivative of the velocity, which would be the acceleration function. Okay. So height is also the same as position. Okay. So some places they talk about height, other places they talk about position. It's basically the same thing. Okay. So height is the original equation or position. Velocity is the first derivative of that, and acceleration is the second derivative. So if you're given velocity, the first derivative of velocity is acceleration. Okay. Get those through your head. And then once you understand that, makes today so much easier. Now, we're going to talk about slope in context of word problems. So here's a word problem. Water is filling a pool. The function W gives the water's level in meters after t minutes. Okay, so the level is your original function. W is the original function. What is the slope of the line tangent to W, the graph of W at t equals 5 is equal to 0.1? What does that mean? Well, the slope of W is the first derivative of W, okay? So at 5 seconds, the slope is 0.1. What does that mean? Well, after 5 minutes, the pool is being filled at a rate of 0.1 meters per minute. That is what it is. It's not 0.01 divided by 5 meters per minute. It's not the level of the water is 0.1 meters. Okay, the level of the water would be what W is. This is how fast it's filling. And it's not being filled at a rate of 0.1 minutes per meter. So you have to really be careful and watch your labels. So after you do 3 problems, you hit this problem and you go, oh, that's what it is. And then you didn't read this, you get really mad because then you have to do all 4 of them over again. Okay, so don't do that. The length of a day in Juneau, Alaska. So if the first derivative of 10 equals 3, D is the number of days. Okay, that's the 10th day. And the length of the day in minute is 3. So now, not the length of the day, the change in the length of the day is 3. Okay, that's the change in, because slope is change in. Okay, so on January 10th, the day is increasing at 3 minutes per day. Yep, the day is not 3 minutes long. The length of the day is whatever D is. Okay, it's not increasing at a rate of 3 days per minute. Okay. And it's not until January 10th, it's on January 10th. The population of a town T years after it's founded. At T equals 2 is equal to negative 10. So 2 years after it is founded, the negative 10 talks about how many people it is increasing or decreasing by. Well, after 2 years, the town's population decreased by 10 people per year. Now, the per year, what does that relate to? That relates to acceleration, okay? Because, yeah, it relates to acceleration. Okay, so position is where you're located. That's the original function. Velocity is the first derivative. Acceleration is the second derivative. So we're going to look at position versus time graphs, okay? This is where you start. Let's say you go to the west by 3 miles. Then it looks like that. Then you go back to where you start. Then you go back, then you go east 3 miles. Then you go back to where you start. Okay? That's moving forwards and backwards. So here you're moving forwards. Here you're moving backwards. Here you're moving backwards. And here you're moving forwards. Okay? So what would that be like? Let's say 3 is like steps. Okay? West is that way. So let's say I start out here. Okay? This is my position at the start, next to Carson. If I go 3 steps forward, I went west 3 steps. Then I go 3 steps backwards. Then I'm back to home again. If I go another 3 steps backwards, I went to the east. And then I'm here. And I go 3 steps forward. And back to Carson again. That's what that graph was. Okay? I went forward still to west, then backwards again, then forwards. Okay? That's the backwards versus forwards on a position versus time. So we're going to have more than just position versus time. Oops. We're also going to have velocity versus time graphs. Now, on a velocity versus time graph, that's a little different. Okay? Velocity is you're going faster and then you're going slower until you go 0. This whole thing, you're going forwards on velocity versus time. Where on position versus time, you only go forward when the slope is positive. Okay? And when the velocity is negative, you're going backwards. Okay? So that's the forward versus backward stuff. Now, let's look at the speeding up, slowing down. Obviously, when you're going positive, you're speeding up here. And then you'd be slowing down here. When it's negative, it's a little more confusing. You're actually speeding up here because you're going from 0 miles per hour to like negative 3 miles per hour. So you're actually speeding up. And then as you go towards the x-axis, you're slowing down. Okay? So you have to understand speeding up, slowing down for the velocity versus time graph. Okay? So we're going to look at a lot of different graphs. Now this is a position versus time, this first one. So it's like this one. Okay? So in position versus time, we're going to look at the moving forwards, moving backwards. Okay? If the slope is negative, we're moving backwards. If we're stopped at a position, it's neither. So we're moving backwards, moving backwards, moving backwards, neither. Got it working? Was it the box or was it the plug-in? Yeah, yeah. So that's what I figured, something like that was it. Okay, thank you.
Yep, no problem.
All right, the next one is a velocity versus time. So you have to understand what type of graph you're looking at. Velocity versus time or position versus time. Okay. The first one, if you're on the x-axis, you're not moving. Okay? So you're not moving forwards or backwards. You're stopped for that instant. Okay? All right. Then, if you're below the x-axis, you're moving backwards. If you're above the x-axis, you're moving forwards. And if you're below the x-axis, you're moving backwards. Okay? And then speeding up or slowing down. If you're going away from the x-axis, you're speeding up. If you're going towards the x-axis, you're slowing down. So here we're going away from the x-axis, so we're speeding up. Here we're going towards the x-axis, so we're slowing down. Here we're on the x-axis, so we're not speeding up or slowing down. We're stopped. When we're on the x-axis for a velocity versus time graph, we're stopped. We're not moving forward, and we're not going backwards, and we're not speeding up. We're not slowing down. But if we're going towards the x-axis, we're slowing down. Okay? So you'll see a bunch of little graphs like that you'll have to interpret. Okay? And when I first saw them, the first year I was teaching this, I had no clue what was going on. But I think I've got it down good enough, and hopefully you get it down good enough now. All right. So once we're through with the graphs, we kind of understand what's going on. A particle moves along the x-axis. Okay? What is a particle's velocity at time equals 2? This is a velocity function. So what should you do with the 2? Well, you plug it straight in. It's 2 to the 4th minus 8 times 2 squared plus 20. 2 to the 4th is 16 minus 32 plus 20. So that's like 4. So the velocity of the particle at 2 is 4. What's its acceleration at 2? Well, acceleration is the what of velocity? Acceleration is the first derivative of velocity. So it would be 4t cubed minus 16t. So if you put in a 2, 4 times 2 cubed minus 16 times 2 is 4 times 8 minus 16 times 2, which is 32 minus 32, which equals 0. Is it speeding up, slowing down, or neither? Neither. Okay. Actually, no. Its acceleration is not changing. It's not accelerating. Acceleration is 0. Its velocity is in a positive direction. So its velocity is 4, so it's neither. Yeah. I had to think about that for a second. Okay. Now, this one is the position. Okay. So we want to find the velocity at 1. So what do we do with the position function? First derivative of that. So it's 4t cubed minus 6t squared plus 6t. So if we put in a 1, we get 4 minus 6 plus 6, which is 4. Velocity at 1 is 4. What direction is the motion? Well, if it's positive, it's moving to the right. positive velocity is to the right, a negative velocity is to the left. Okay, and then some of these word problems get a little confusing. Max wrote an algorithm that searches for a specific term within a large set of terms. The following function gives the length of the search in the number of steps over the set of n terms. What's the instantaneous rate of change for a certain length of a set of 10 terms? So this is the original function. Okay, that's the original function. So it's the rate of change is the first derivative of this. So what would be the first derivative of this? Well, it's 1.6 times, what's the first derivative of a natural log? 1 over that, 0.9n times the first derivative of the inside, because it's a chain rule, which is 0.9. What happens to 0.9s? They cancel. So it's 1 over n. If we put in a 10, it's 1.6 over 10. 0.1 step, because it says the following function in the number of steps over a set with m terms. So I think it's 0.16 steps per term for a set of n terms. Yeah, because it doesn't talk about time at all. It talks about steps. So it'd be 0.16 steps per term. The following gives the cost in dollars of producing X gallons of wood stain. What's the instantaneous rate of change when 100 gallons are produced? Well, instantaneous rate of change is the first derivative. So it's 0.0012x squared minus 0.002x plus 0.1. We put in 100 in here and 100 in here. 100 squared is, I don't know, 10,000 times that is like 12 minus 0.2 plus 0.1, which is 11.9. So it's $11.9 per gallon, because it has to be per something, because we're the first derivative, this per this. Vera studies the extinction of the bear population of Siberia over time. The following function gives the number of bears T years since Vera started tracking it. What's the instantaneous rate of change in the number of bears after 2 years? So we have to take the first derivative of this, which is negative 0.3 times 2190 times e to the negative 0.3 t power, because it's the first derivative of this is this times the first derivative of the top. So that's why I did it that way. So negative 0.3 times that, I would guess it's 361, right? Negative 361. So that would be bears per year, not years per bear. Okay, so that's the types of problems that you'll see today.
Yay!
So that's all we're doing today.